from freshman year what power is? No. Hint, it has something to do with work. I still need to go borrow some of my Schaefer's crickets apparently. All right, so work is what? Work is
the amount of force it takes to move something.
not quite. It is force times distance. Work is actually the energy necessary to move it. So it's the energy necessary to apply that force over that specific distance. Okay? So work is energy. So it's good to know how much work we have to do, but are you going to feel different if you walk up a hill or run up a hill?
Yes.
Yeah, you're going to feel different after doing both of those. In both cases, you might be running up the same hill, and so we know we've done the same amount of work against gravity, right? We're going to ignore non-conservative forces for this example. So if you've done the same work, why do you feel different?
You use more energy.
No,
More power.
you use more power. So what was the difference between those situations? We used the same amount of energy, but what thing changed? What's the difference between walking and running?
One's faster.
Okay, time is going to be what is affected here. Okay, so if you run up the hill, you're going to use the same amount of energy in a much smaller amount of time than if you walk up the hill. Okay, so because of this, we know that how fast we use that energy is going to be important, and that is what power is. So this is the rate at which you are using that energy. In this case, we are going to talk about average power because we can't do integrals and fun stuff like that. So, it is fun though.
Sounds too smart for me.
Let me make sure I do it similar to the way they have. Yeah. So this is your average power. It is the average rate at which your energy is used or your work is done. Okay? Obviously, if we were using calculus, since this is a rate, we would probably take the derivative of work with respect to time, and we would get the true power at any time we want. Okay? So all you would have to do there, if you have an equation, this is actually a really good example of what I was talking about yesterday. For those of you who weren't here, I talked about how calculus and physics work really well together. Finding an equation for our force is generally not super hard, okay? Even if we're going to a more complicated force like the magnetic force, so a magnetic field force, we actually have a pretty well-defined equation for what our force is going to be, okay? So what we could do is take our equation for our force. We're going to assume this is our equation. Cool. We would multiply that by our distance. Actually, we'll do this super official. We'll have the cosine theta in there and our distance, right? Yeah. Then what we can do is, this is our work, right? So if we take the time derivative of our work, we get our instantaneous power, right? Yeah. So d dt of this thing is going to give us power. The thing that makes calculus so much better is taking the time derivative of this thing is generally actually pretty easy. Not always, but it's pretty easy. We just have those shortcut rules. Those of you in calculus probably are familiar with most of those. And we get an equation out. That means that we can figure out how much power we've done in any amount of time. And we no longer have to worry about that average. Is that going to make sense? Okay. So this is the calculus version. Sadly, we're not doing the calculus version. I know Nick is crushed.
I am crushed.
Okay.
I love learning calculus.
Yep.
I don't understand.
So instead of taking the time derivative, which would give us the actual rate at any point, we are just going to divide by time because we are taking our average. So work is going to be, power is going to be work divided by time. Okay, good. If you look in your book at the equation, there is a little line over the P like this. That means that it's your average quantity. Okay. Physicists really like putting little things over the letters. The arrows show that they're vectors. Sorry. Lines show that they're averages. Once you start getting into calc-based physics, you can actually put dots to show that it's a time derivative and things like that. Cool? All right. So to find our power, all we have to do is take our work divided by time. In some cases, it might be easier to write it like that. Cool? So work is not anything too crazy complicated, or power is not anything too crazy complicated. Once you know how to calculate work, calculating power is not very hard. Good? Okay. So, let's see. What would be a good example for this? Oh, hey, I should probably tell you what units power is in, right? Okay, so this is going to be in joules per second, right? It is spelled differently, just in case of what you were thinking. So joules per second. Then this is the derived unit of the watt. Okay. It is named after a person, like a lot of these units. So the abbreviation for it is a capital W. Good? Any questions on that? No? Okay. All right. Let's see here. We'll start with an easy one. Everybody have this written down? Let's say that we have the example with the hill, like I said. Okay? So we have a hill that is, how tall do you want the hill to be?
200 feet.
200 feet? Let's do meters, because then we don't have to do conversions.
Good idea.
Okay. All right, so we've got 200 meters. So it's definitely not a small hill. Okay? And let's say we have two people. This person, okay, is going to, actually, let's make them identical twins. Okay, so they have the same mass, because that's going to affect things. All right. How much do they, not weigh, how much is their mass?
100 kilograms.
100 kilograms. So that person and that person are both 100 kilograms. Okay? Let's say one of them decides they're going to go up this hill really, really slow. And the other one is going to do that thing that I'm sure your siblings have definitely done to you, or you've done to your siblings, where you start running and then you say that it's a race after you start running. Yeah? Everybody knows that trick? Yep.
That's what me and my sister always do, like, after we leave.
Yep.
I messed up, and I would always win.
So, this person's going to start running up the hill. How long does it take him to get up the hill, do you think?
30 minutes.
30 minutes. Okay.
It's a big hill.
We're going to have to convert again because it's per second. So,
We can figure that out.
I mean, it's not hard, but we will have to convert. So 30 minutes.
No.
Yeah, right.
It's times 60, which is, okay, so it's going to take this guy 1,800 seconds. This guy's going to walk up the hill. How long does it take him? Probably more than 1,800 seconds if our example's going to make sense. 18,000 seconds.
32,000. How is it? Yeah.
Slow down. That's a big hill.
He's just taking his
200 meters?
Yeah.
I mean, it's not a small hill, but I don't think it's quite that big.
Yeah, no, it's swim that. in 2
All right.
minutes.
Under.
No, you know we can't.
Don't forget that this is the height of the hill, not the length of the hill. Okay? So it's not the hypotenuse of the triangle, it's the height of the triangle. All right. So we're going to calculate how much work these guys, or no, how much power they used. Okay? So our power, we're going to call it average, is our work divided by our amount of time. In this case, we're just talking about our work from gravity. So what equation do we probably want to use for our work? MGH. So we get our mass times the acceleration of gravity times the height of the hill, and then divide that by the time. Okay? So for our person, we'll call this person number 1, this person number 2. So power of person 1 is going to be 100 kilograms times 9.81 meters per second squared times 200 meters divided by 1,800. Second person is going to be same numerator. But this time divided by 32,000 seconds. Okay? So what do we get? Apparently more crickets.
I got 109 for the. I got that as well.
109 for the first one.
Oh, I just marked out the most.
You can't even access forms on here. Like you can't access grades.
Uh-huh.
Yeah. 6.13. And like I have a single class tonight and I'd like to study for it, but I can't get on campus.
I mean, you did go look up the thing that they specifically said was blocking everything on their computer.
I didn't look at, no, that's not good.
Is it just everything blocked now?
Yeah, it's everything.
Oh, okay.
All right. So, which one used more power? Okay, we use more power here than we did here, even though we have done the same amount of work, right? Okay, So your rate of how fast you go is going to tell you that you're going to use more power. Good? Okay. We know that this is important because we can feel the difference between running up a hill or walking up a hill, or even just running anywhere, right? Because we're doing that work faster, we're obviously going to use more power than if we just walked up the hill or whatever it was. Okay? All right. Any questions on this? No? Okay. Like I said, power is not super complicated. We are pretty darn close to the end of the chapter, so we might actually have a test. I know. It's crazy thoughts. So, we will probably have a test over work and power. So yeah. Do you guys have any questions before I turn the live stream off?
Yes. How dare you?
I'm a teacher. It's what I'm supposed to do.
We do have a problem. That team doesn't get tests.
Yeah.
Hey, I have not given you a test at all this semester so far.
It helps. It helps.
You did know that.
Yeah.